Imagine the relentless roar of a race car engine, the comforting warmth from your morning coffee, or even that burst of energy you feel after a really satisfying meal.
Yeah.
What's the hidden thread connecting all these, well, seemingly different experiences?
It's energy, right?
It's all about how energy moves, transforms, and is contained within what we call a closed system.
Exactly. Fixed amount of stuff, energy moving in and out.
Welcome to the Deep Dive. Today we're taking a plunge into a really powerful concept from the world of thermodynamics.
That's right. We're looking at energy analysis of closed systems.
Our mission really is to cut through the complexity of the research here and pull out the most important actionable insights.
Giving you a crystal clear understanding, hopefully.
Yeah, of these fundamental energy principles that literally govern everything around us. From the machines we build to the very processes happening inside your own body.
We'll explore how we define and measure energy and the fascinating ways it interacts in systems where the mass stays fixed.
Get ready for some unexpected revelations, practical wisdom, and those genuine aha moments that make complex science feel, well, incredibly clear and relevant to your everyday life.
Let's hope so.
So let's kick things off with a concept you already interact with constantly, maybe without even realizing it. The idea of work.
Right. Not just like going to the office work, thermodynamic work.
Exactly.
Yeah.
Think about a car engine. Combustion gases push a piston, right? And that push causes motion.
That's a perfect start. This isn't just movement. It's a prime example of what we call moving boundary work.
Moving boundary work.
Yeah, this kind of work is directly tied to a system either expanding or compressing.
Like the gas in the cylinder.
Precisely,
Yeah.
which is why it's so fundamental to devices like piston cylinder engines and pumps. It's often simplified to thinking about PDV work.
PDV. Pressure times the change in volume.
Exactly. Pressure times a tiny differential change in volume. Essentially, it's the work done when a boundary, like that piston face, moves.
Okay, now real engines are chaotic, aren't they? Pistons moving super fast, friction, heat loss.
Yeah.
It's messy.
Oh, absolutely. Very complex.
So how do thermodynamicists even begin to analyze something like that? Does all that simplification mean we lose touch with reality?
That's a really good question, and it's a crucial distinction. While real-world scenarios are indeed complex, far from perfect,
Yeah.
thermodynamics often analyzes what we call quasi-equilibrium processes.
Quasi-equilibrium. Sounds fancy. Slow processes.
Kind of. It's a theoretical ideal where the system is always infinitesimally close to equilibrium. Imagine it moving slowly enough for properties like pressure and temperature to be uniform throughout at any given instant.
Okay, so it's a model.
Exactly. We use this simplified model precisely because it sets the benchmark. It helps us understand the absolute theoretical maximum work an engine could produce.
The ideal limit.
Or the minimum work a compressor would need, theoretically. It gives us a target to aim for, even if reality always falls a bit short. It's the perfect blueprint we compare everything else to.
Right. And this next part is where it gets really visual, I think. Imagine plotting the journey of that gas as it expands or compresses. If you graph its pressure against its volume, what we call a PV diagram.
Yes, the pressure volume diagram. Very important tool.
The area under that curve directly tells you the amount of boundary work done.
Exactly. This diagram isn't just a fancy graph. It's like the hidden blueprint for every engine. And it highlights a critical point about work. It's a path function.
Path function. Meaning?
Meaning the amount of work isn't just determined by where you start and end, your initial and final states. It depends entirely on the specific route or path the process takes between those states.
Okay, so how you get from A to B matters.
Tremendously. It's why car engines or power plants can produce network over a complete cycle. If work didn't depend on the path, any work produced in one part of the cycle, say expansion,
Would just be canceled out by the compression part?
Exactly. You'd never get any useful output. The clever part is designing a cycle where the expansion path encloses more area on that diagram than the compression path. That difference, the area inside the loop, gives you a net gain.
That's the secret sauce for power.
That's the secret sauce, yeah.
So let's make that more concrete. What if you have something like, say, air cooling down in a rigid sealed container? No moving parts, no change in volume.
Right.
What's the boundary work there?
Zero. Simple as that. If the volume can't change, if dV is 0, then P times dV is 0. No PdV work can be done.
Like a pressure cooker, once it's sealed.
Perfect example. Its volume is fixed. Any energy added or removed isn't doing work on its boundaries. It's just changing the internal energy, the temperature, the pressure inside.
So a constant volume process means zero boundary work. Simplifies things.
Immensely.
Okay, that makes perfect sense for a rigid container. But what happens when volume does change? Maybe in a more predictable way, like if the pressure itself stays constant throughout the process.
Constant pressure process.
Yeah.
Very common.
Say, steam expanding in a frictionless piston cylinder device.
In that situation, the work done is beautifully straightforward. It's simply the constant pressure multiplied by the total change in volume, P times V2 minus V1.
So if steam expands and pushes the piston out.
The system is doing positive work on its surroundings. It's expending its own energy to achieve that expansion. Very common in many industrial applications like boilers or turbines.
Okay. And what if we have an ideal gas, compressing or expanding, but its temperature stays perfectly constant? An isothermal process.
Right. Isothermal means constant temperature. For an ideal gas doing that, the relationship for work involves a natural logarithm function of the volume ratio, V2 over V1.
So a bit more math involved there.
A little bit, yeah. But the conceptual takeaway is that you can still calculate the exact work involved, whether it's work being done by the system during expansion or work done on the system during compression.
Okay. We've talked constant volume, constant pressure, constant temperature. But what about a more general scenario, something that covers a lot of real-world situations maybe?
That's where polytropic processes come in. It sounds complicated, but it's really just a mathematical relationship, PV to the power of n equals a constant.
PV to the n.
Yeah, where n is some exponent. This describes a broad class of processes where pressure and volume are related by this general power law. It covers the other cases too, actually, like N0 is constant pressure, NaO1 for an ideal gas is isothermal, and then going to infinity is constant volume.
Ah, okay, so it's a flexible model.
Very flexible. It allows for a more comprehensive calculation of boundary work for systems that don't perfectly fit those simpler conditions. Makes our models more versatile.
And one more case. What if our gas is expanding not just against the atmosphere, but also against something like a spring, like in a piston cylinder with a spring attached?
Oh, that's an interesting one, because
Yeah.
the pressure isn't constant anymore, is it?
No, the spring pushes back harder as it compresses.
Exactly. As the gas expands, it compresses the spring, and that spring's force, and therefore the pressure it exerts back on the gas, increases, usually linearly.
So on that PV diagram,
It wouldn't be a simple horizontal line for constant pressure. It would be a sloped line, typically straight if the spring is linear. The whole process might look like a trapezoid on the PV diagram.
okay, and the work.
The total boundary work is just the area under that sloped line, the area of the trapezoid. And you could even break it down mentally into two parts,
Right?
like the work done just pushing the atmosphere out of the way, which is like the constant pressure part.
The rectangular bit underneath.
Yeah. And then the additional work done specifically against the increasing force of the spring, that's the triangular bit on top, shows how we can analyze more complex combined forces.
Okay, let's unpack this a bit further then. If work is one critical piece of the energy puzzle,
A very important piece.
what's the grand overarching principle that governs all energy movement? That brings us to the bedrock of thermodynamics, right? The first law.
That's the core of it all. The first law of thermodynamics is really just a statement of the conservation of energy principle. Simple, but profound.
Energy can't be created or destroyed.
Nope. In its simplest form, it says, energy in, energy out. Change in system energy. Or ein out equals delta E system.
Like your bank account analogy.
Exactly. Deposits minus withdrawals equals the change in your balance. Energy just gets moved around or changes form.
And for a closed system, remembering,
Yeah.
that means a fixed amount of mass, nothing crossing the boundary except energy.
Right. Fixed mass.
How does energy get transferred across its boundaries?
For a closed system, energy crosses the boundary in two main forms we care about. As heat, symbolized by Q,
Which is driven by a temperature difference.
correct, or as work, W, which we just spent a lot of time discussing, boundary work, shaft work, electrical work, etc.
Heat and work.
Yeah.
Q and W. Those are the transfers.
Those are the transfers across the boundary, yes.
And what about the energy inside the system? What kinds of energy can change? That delta E part.
Precisely. The total energy stored within the system, that change in system energy, delta E, can manifest in a few ways.
Yeah.
Primarily, it can be a change in its internal energy, usually symbolized by U. That's the microscopic energy, molecular vibrations, rotations, chemical bonds. often tied closely to temperature.
Okay, internal energy U.
Or if the whole system is moving faster or slower, it could be a change in its kinetic energy, Ke.
Right.
And if its elevation changes in a gravitational field, a change in its potential energy, Pe.
So delta E equals delta U plus delta Ke plus delta Pe.
That's the full picture. Although, for many stationary closed systems we analyze, the kinetic and potential energy changes are zero or negligible.
So often it just boils down to delta U.
Very often, the first law for a stationary closed system simplifies to Q minus W equals delta U. Heat in minus work out equals the change in internal energy.
And what about systems undergoing a full cycle, like that engine we mentioned, where it returned to its initial state?
For a cycle, the end state is identical to the start state. So all the properties, including internal energy, kinetic, potential, they must return to their original values.
Meaning delta E for the whole cycle is zero.
Exactly. So if ein out equals delta E, and delta E is zero for a cycle,
Then I must equal EAT. Energy in equals energy out over the cycle.
precisely, which means the net heat input, QNet, must exactly equal the network output over the cycle. That's fundamental to how heat engines operate.
It's remarkable, isn't it, that from the first law's perspective, heat and work seem to be just. Different labels for energy crossing a boundary, they seem interchangeable in the balance sheet.
It's true. From a pure energy accounting standpoint, the first law treats them sort of equally. A joule of heat is equivalent to a joule of work in that energy balance. They both contribute to that conservation principle.
Also, you sense a but coming.
Yeah, yes. And this is a fascinating nuance, maybe something for a future deep dive. From a second law perspective, heat and work are very different.
How so?
In terms of their quality or usefulness, you can convert work entirely into heat. Pretty easily, think friction. But you can never convert all the heat supplied into useful work, not even in theory. There are always limitations.
Okay. So the second law brings in ideas of efficiency and direction.
Exactly. But for the first law, for just balancing the energy books, Q and W are simply the ways energy gets across the system boundary.
Okay. This raises an important practical question. How do we simplify our calculations for specific scenarios? For constant pressure processes in closed systems, the research introduces this concept called enthalpy.
H,
Yes.
enthalpy, defined as H equals U plus PV, internal energy plus the product of pressure and volume.
Why is that so incredibly convenient, especially for constant pressure situations?
Enthalpy is, well, it's kind of a genius bookkeeping trick for constant pressure processes. The reason it's so convenient is that the boundary work done during that constant pressure expansion or compression, which is P times delta V, is automatically accounted for within the change in enthalpy equal delta H. Remember, H is U plus PV, so delta H is delta U plus delta PV. If P is constant, delta H is delta U plus P delta V.
And P delta V is the boundary work.
Exactly. So delta H equals delta U plus the boundary work, WB. If you plug that into the first law for constant pressure, Q whether WB equals delta U, the WB and P delta V terms combine beautifully.
Meaning
For a constant pressure closed system process, the heat transfer, Q, often equals the change in enthalpy, delta H, especially if there's no other work like shaft work involved. Q equals delta H.
So instead of calculating internal energy change and boundary work separately,
You just look at the change in enthalpy. It streamlines the energy balance tremendously for many real-world applications, like heating water in an open pot or in a boiler. You simply focus on heat added or lost, and that directly tells you the change in enthalpy.
that is convenient. Now, you also mentioned something earlier that sounded almost like an oxymoron. Zero work expansion.
Right, sometimes called unrestrained expansion.
How can something expand, change its volume, without doing any work?
It seems counterintuitive, doesn't it? But imagine a gas confined to one side of a rigid container with a vacuum on the other side, separated by a membrane. Now, rupture the membrane. The gas expands rapidly to fill the whole container. Its volume changes dramatically.
Right.
But what is it pushing against?
Nothing. A vacuum.
Exactly. There's no external pressure, no resistance from the surroundings to push against or overcome. Since work involves a force acting over a distance or pressure acting against a moving boundary, if there's no resisting force or pressure.
Then no work is done by the system, even though it expanded.
Correct. W is zero in that specific scenario. It's a critical distinction to grasp in understanding how work is defined. It requires interaction with the surroundings.
Okay, that makes sense. Let's shift gears slightly. Have you ever noticed how quickly, say, A thin metal pan heats up on the stove compared to a large pot of water.
Oh, yeah, definitely. It takes ages to boil water sometimes.
Right. It takes vastly different amounts of energy to raise the temperature of identical masses of different substances by the same amount, say 1 degree Celsius.
That's a fantastic observation, and it perfectly illustrates the concept of specific heat.
Specific heat, so it's specific to the substance.
Exactly. It's formally defined as the energy required to raise the temperature of a unit mass of a substance by 1 degree. Different materials have different capacities to store thermal energy.
And in thermodynamics, we talk about two main types.
We generally focus on two: specific heat at constant volume, called CV,
Okay.
and specific heat at constant pressure, called
CV and CP. And there's a fundamental reason why cheap is always greater than CV, right?
Yeah,
What's the physical story there?
absolutely. Think about heating a substance. If you heat it at constant volume, like in that rigid tank we discussed,
Yeah.
all the energy you add goes directly into increasing the internal energy of the molecules, making them vibrate faster, move faster, whatever. That increase in internal energy shows up as a rise in temperature.
Okay, all energy goes to internal energy.
Right. Now, if you heat it at constant pressure, like in a piston cylinder device where the piston is free to move.
The substance can expand.
Exactly. As you add heat and its temperature starts to rise, it will likely expand to keep the pressure constant. And doing that expansion requires work, boundary work, pushing against the surroundings.
So some of the energy is used up doing work.
Precisely. So at constant pressure, some of the energy you add goes into doing that expansion work, in addition to increasing the substance's internal energy.
Which means you need to add more total energy to get the same temperature rise compared to the constant volume case.
You got it. Since Cl is the energy needed per degree at constant pressure, and CV is the energy needed per degree at constant volume, CP must be greater than CV because of that extra energy needed for expansion work.
That makes intuitive sense. Now, what's fascinating here, as the research points out, is that even though their names come from specific processes, constant volume, constant pressure, CD and CB are actually fundamental properties of the substance itself, almost like its density or molecular weight. They aren't just tied to those specific processes.
That's a crucial distinction, and it's a really profound insight, especially when you deal with ideal gases. For an ideal gas, the change in internal energy, delta U, always depends on CV, regardless of the process.
Even if the volume wasn't constant.
Even if the volume wasn't constant, delta U for an ideal gas is always the integral of CV dt. And similarly, the change in enthalpy, delta H, for an ideal gas always depends on a HIP, regardless of the process. Delta H is the integral of Cp dt.
Wow. So they're inherent characteristics that tell you how a substance's internal energy and enthalpy respond only to temperature changes, at least for ideal gases.
Exactly. They are true thermodynamic properties.
Speaking of ideal gases, many common gases, like air, especially at lower pressures and higher temperatures, behave remarkably like these theoretical ideal gases. What's the magic behind that model? Why is it so useful?
The ideal gas model is a simplification, sure, but it's incredibly useful because it captures the essential behavior of many real gases with surprising accuracy under many conditions.
And the core idea is that simple relationship between pressure, volume, and temperature.
Right, the ideal gas equation of state. PV equals MRT, or PV equals RT, where V is specific volume. It assumes molecules have negligible volume themselves and don't interact except for perfect elastic collisions.
And this leads to that really pivotal point you just touched on. For an ideal gas, internal energy and enthalpy depend only on temperature.
Yes, this is huge. It was famously demonstrated experimentally by James Joule.
What did you do?
Essentially, he had two connected tanks, one with air under pressure, the other evacuated. He put the whole thing in a water bath to measure temperature changes. When he opened the valve, the air expanded into the vacuum and unrestrained expansion.
Like we discussed before, zero work done.
Correct. And he measured basically no change in the water bath temperature, meaning very little heat transfer. Since Q is close to zero and W is zero, the first law, QW equals delta U, told him that the change in internal energy, delta U, must also be basically zero.
Even though the pressure and volume changed dramatically.
Exactly. The only thing that hadn't changed significantly was the temperature. So he concluded that for a gas like air, internal energy must be a function of temperature only. And since enthalpy H equals U plus PV, and PV for an ideal gas is RT, enthalpy also depends only on temperature, H equally T plus RT.
That's a game changer for calculations, isn't it?
Absolutely. Because of this unique temperature-only dependence for ideal gases, calculating changes in internal energy and enthalpy becomes incredibly simple. You don't need to worry about the pressure or volume changes directly.
So delta U is just related to CV and delta T and delta H to CP and delta T.
Pretty much. More precisely, delta U integral CV dt and delta H equals integral CB dt. But if the temperature change isn't too large, you can often approximate CV and CP as constants, using average values for the temperature range.
Which gives us delta U is approximately CV, average times delta T, and delta H is approximately CP, average times delta T.
Exactly. Those are incredibly useful approximations for quick calculations. It dramatically simplifies things compared to dealing with real gas tables or complex equations of state.
So if you're working with an ideal gas, you basically have a few ways to figure out these energy changes, delta U and delta H.
That's right. You've got options depending on the accuracy you need.
Like,
Well, method one, the most accurate generally, is to use tabulated values of U and H if they're available for your gas. These tables are generated using the actual variations of specific heats with temperature.
okay, the tables.
Method two is to integrate the specific heat functions. If you have an equation for how CV or heat changes with temperature, you can perform the integration, often numerically with computers, to get the exact delta U or delta H.
Right, using the integral definitions.
And method three, the simplest, is to assume constant specific heats, usually evaluated at some average temperature, and just use delta U equals CV delta T and delta H equivalent CP delta T.
Quick and often good enough.
Often surprisingly good, especially for moderate temperature ranges or for monatomic gases where specific heats vary very little. This flexibility makes ideal gas analysis incredibly powerful.
And there's some core relationships that always hold true for ideal gases, linking CP, CV, and the gas constant R.
Definitely. One fundamental relationship is that CP equals CV plus R. The difference between the specific heats is just the gas constant for that particular gas.
CP is CV plus R.
Okay. And there's also the specific heat ratio, often denoted by K, sometimes gamma. It's defined as K equals CPCV.
KECPCV. What's typical for that?
For monatomic gases like helium or argon, K is about 1.67. For diatomic gases like air, mostly nitrogen and oxygen, at room temperature, K is typically around 1.4. It pops up in equations for certain types of processes like adiabatic ones.
Got it. These relationships are workhorses for quick calculations then.
Absolutely. Very handy.
Let's maybe look at some real-world examples with ideal gases to see this in action. What happens if you, say, stir gas, maybe helium, in a rigid insulated tank with a paddle wheel?
Okay, so rigid tank means?
Constant volume, zero boundary work.
Right. And insulated means?
No heat transfer. Q is zero.
Good. So the first law becomes QW equals delta U, which simplifies to 0W equals delta U, or W equals delta U.
The work done by the system is negative delta U, or the work done on the system.
The work done on the system by the paddle wheel, let's call it W paddle, equals the increase in internal energy, delta U.
The stirring it adds energy.
Yes. All the mechanical energy put in by the stirring paddle gets dissipated into the gas, increasing its internal energy.
And for an ideal gas, internal energy means temperature.
Exactly. So stirring the helium makes its temperature rise. And since the volume is fixed, the pressure will also increase according to the ideal gas law. It's a clear example of work directly converting to internal energy.
Okay. What if we introduce an electric heater into a piston cylinder device? Let's say it contains nitrogen gas, and the piston keeps the pressure constant.
Ah, okay. Piston cylinder, constant pressure. This screams enthalpy.
Right. So you're putting in electrical work with electric.
Yes, that's energy coming into the system as work.
And maybe there's some heat loss to the surroundings, quote.
Okay, heat leaving the system.
And the gas expands at constant pressure doing boundary work, WB.
Right. So the full first law is energy in, energy out, change in energy. So electric, in quote, plus WB, out, delta U.
Okay, that looks a bit messy.
But wait. Remember, for a constant pressure process, delta H equals delta U plus WB. We can rearrange the first law to electric quote equals delta U plus WB.
Which equals delta H.
Bingo.
Yeah.
So the net energy added, electrical work in minus heat loss out, equals the change in enthalpy of the nitrogen gas. Electric quote equals delta H.
Much cleaner.
Much cleaner. And since delta H for an ideal gas is just Cp delta T approximately, you can easily find the final temperature if you know the energy inputs, outputs, and Tp. Enthalpy makes constant pressure analysis much slicker.
That's great. And what about a more complex, multi-stage process?
Yeah.
The outline mentions air in a piston that hits some stops partway through heating.
Oh, yeah, those problems are classic. They really test your understanding of applying the principles stage by stage.
So what might that look like?
Imagine you start heating air in a piston cylinder. Initially, maybe the piston rests on some stops, so the volume is fixed.
Stage 1, constant volume heating.
Right. You add heat, Q1, volume is constant, so boundary work, WB1 is 0. The energy balance is Q1 is 4 delta U1. Pressure and temperature increase.
Until
Until the pressure is high enough to lift the piston off the stops. Let's say that requires a certain pressure P2.
Okay, so now the piston can move.
Now let's say you continue heating. If the external pressure, like atmosphere plus piston weight, is constant, the air will now expand at this constant pressure P2.
Stage 2, constant pressure expansion.
Exactly. You add more heat, Q2. Now there's boundary work, WB2 equals P2, V3, V2. The energy balance for this stage is Q2, WB2 equals delta U2, or more simply, Q2 equals delta H2.
Enthalpy again, because it's constant pressure.
Right, so the total heat added is Q1 plus Q2. The total work done is just WB2 since WB1 was 0. And the total internal energy change is delta U1 plus delta U2.
And you can calculate everything using specific heats and temperatures at each state.
Precisely. It really demonstrates how you apply the first law and the concepts of work and heat transfer piece by piece through a complex sequence of events. It shows how heat, work, and internal energy dynamically interact.
Okay, that covers ideal gases pretty well. Now, what about solids and liquids? How do we handle energy analysis for them?
Well, the good news is that for many common thermodynamic analyses, solids and liquids are often much simpler to deal with than gases.
Simpler. How so?
We often approximate them as incompressible substances.
Incompressible, meaning their volume doesn't change much.
Exactly. It means their specific volume or density remains nearly constant, even with significant changes in pressure or temperature. Think about water. You have to apply enormous pressure to compress it even a tiny amount.
Right, compared to air, which is easily squashed.
Precisely. And this assumption makes a huge difference.
Okay, so what's the result of assuming they're incompressible? Does it affect specific heats?
It does, in a very simplifying way. Remember, couple is greater than CV because of expansion work? Well, if a substance is incompressible, it basically can't expand or contract. Delta V is essentially 0.
So the expansion work term disappears.
Exactly, which means the distinction between heating at constant volume and heating at constant pressure becomes meaningless. They require the same amount of energy.
So CV and CP become the same.
For a truly incompressible substance, yes. CV equals CP, so we can just drop the subscript and talk about the specific heat.
Just CC. That definitely simplifies things.
It really does. One less property to worry about.
So how do you calculate energy changes for them then? Like delta U and delta H?
Since the volume change is negligible, the internal energy U depends almost entirely on temperature, just like for an ideal gas, but even simpler because there's only one specific heat C.
So delta U is just CdP times delta T.
Approximately, yes. Delta U is approximately the integral of CdT, or often just Cavendish delta T. Very straightforward.
And enthalpy, HU plus PV.
Good question. Delta H equals delta U plus delta PV. Since V, specific volume, is approximately constant for an incompressible substance, delta PV becomes V delta P.
So delta H equals delta U plus V delta P.
Correct. Or delta H is approximately K of G delta T plus V delta P.
Is that V delta P term usually significant?
Often, it's very small compared to the C delta T term, especially for processes that don't involve huge pressure changes. For solids, it's almost always negligible. For liquids, you might need to include it if the pressure change is very large, like in pumps. But often, even for liquids, delta H is approximated as just K of G delta T.
So for solids and liquids, energy changes are mostly about temperature changes, driven by that single specific heat C.
That's the main idea, yes. It simplifies calculations considerably.
Let's look at some practical applications. How would we determine the enthalpy of, say, compressed liquid water? Water at a high pressure but below its boiling point.
Okay, so you have water at a given temperature T and a high pressure P. You want its enthalpy H. Well, the most accurate way is to look it up in compressed liquid tables, if they're available.
But if not?
A very common and usually quite accurate approximation is to use the enthalpy of the saturated liquid at the same temperature. HTP is approximately HF at T.
So you just ignore the high pressure. Why does that work?
Because, as we just discussed, the effective pressure on the enthalpy of a liquid, that V delta P term, is often small unless the pressure difference is enormous. Using the saturated liquid value at the same temperature captures almost all the energy associated with its liquid state at that T.
Okay, so H is approximately HF at the given temperature. That's a handy shortcut.
Very handy. Saves looking through bulky compressed liquid tables.
How do these principles apply to something as everyday as mixing hot and cold things? Like dropping a hot iron block into a bucket of cold water in an insulated container.
Ah, a classic thermal equilibrium problem. Insulation means...
No heat transfer with the outside. Q equals 0.
Right, and assuming no work is done, no stirring, etc., W is still 0. So the first law for the combined system, iron plus water, says delta E equals 0.
The total energy of the combined system doesn't change.
Correct. Assuming no significant kinetic or potential energy changes, this means the total internal energy change is 0. Delta U iron plus delta U water equals 0.
So the energy lost by the iron equals the energy gained by the water.
Exactly. Delta U iron is negative, delta U water is positive, and they sum to 0.
And we can calculate each delta U using
Mass times specific heat times temperature change for each substance. Myron siren T final tire initial plus mem water T final twater initial equals 0.
And since we know the initial masses, specific heats, and initial temperatures.
The only unknown is the final equilibrium temperature, T final. You can solve for it directly. It's a powerful demonstration of energy conservation predicting the final state.
Neat. And what about industrial processes? The outline mentions annealing steel balls, heating them up, and then cooling them in air.
Right. Imagine hot carbon steel balls coming out of a furnace at, say, 850 degrees C and being cooled down to 100 degrees C in ambient air. We can think of each ball as a closed system losing energy. The change in its internal energy is, again, delta U equals mc, T final to initial.
We'd need the mass and specific heat of the steel balls.
Correct. If we know those and the temperature change, we know how much energy each ball loses.
And if we know how many balls are processed per minute,
then we can calculate the total rate of heat transfer from the balls to the air. It's just the energy change per ball times the number of balls per unit time. This is a direct, practical application of the first law, delta U and Q, since work is likely negligible, to determine cooling requirements or energy recovery potential.
so these seemingly abstract thermodynamic principles have very direct engineering applications.
Absolutely, all the time.
Okay, so we've covered engines, gases, liquids, solids. What about us? What does this all mean for you, the listener? Can we apply these same powerful thermodynamic principles to the human body?
Oh, definitely. It's absolutely fascinating how these principles scale and apply to biological systems. We can think of the human body as an incredibly complex, sort of closed system for energy analysis purposes.
Closed system. But we eat and breathe.
Ah, good point. Over short time scales, maybe not perfectly closed regarding mass, but if we consider the energy balance over, say, a day, the mass change might be small compared to the energy flows. The key is the conservation of energy still holds.
Okay, so how does energy work in the body?
Our bodies are constantly performing metabolism. That's the sum of all chemical processes. Essentially, we're burning the fuel from our food, carbohydrates, fats, proteins, reacting it with the oxygen we breathe.
To release energy.
Exactly, to release the chemical energy stored in the food molecules. This energy powers everything: muscle movement, nerve impulses, maintaining body temperature, building tissues.
Even when we're just resting.
Absolutely. Even just lying still, your body is expending energy just to keep you alive. Heart beating, lungs breathing, brain functioning. This is your basal metabolic rate, or BMR.
And that's measurable.
Oh, yes. For an average adult male, it's roughly 84 watts. Think about it. It's like having an 84-watt incandescent light bulb running inside you constantly, just for basic maintenance.
Wow. And when we exercise, it goes way up, right?
Yeah.
The research notes 2 people doing strenuous exercise can put out more heat than a 1-kilowatt electric heater.
It's true. Our bodies can be quite powerful energy converters. Most of that energy released during activity ends up as heat.
How does it leave the body?
2 main ways. As sensible heat, just warming the surrounding air through convection and radiation, and as latent heat, which is the energy carried away when perspiration evaporates from your skin. Evaporation requires energy, and it takes that energy from your body, cooling you down.
Right, sweating cools you off.
Precisely. It's a crucial thermoregulation mechanism.
And speaking of energy from food, how is that measured? You can't just put a sandwich in a thermometer.
No. The energy content of food is measured using a device called a bomb calorimeter.
Sounds dramatic.
It kind of is. They place a known mass of the food sample inside a sealed, oxygen-filled container, the bomb, submerge it in a known amount of water, and then ignite the sample electrically.
So they literally burn it.
Completely burn it. And by measuring the temperature rise of the surrounding water, they can calculate exactly how much heat energy was released by the combustion.
And this is where the food calorie comes from, the one on nutrition labels.
Exactly. But there's a common confusion. The calorie used in physics is the energy to raise 1 gram of water by 1 degree C. The food calorie, usually written with a capital C, is actually a kilocalorie, kcal. It's 1,000 physics calories. And 1 calorie, or 1 kcal, is equivalent to 4.1868 kilojoules.
Okay, so 1 food calorie equals 1 kcal equals 4.18 tilde kJK. Good to know.
It's essential for understanding energy values on labels. What's also striking from calorimetry is the difference in energy density between macronutrients.
Like fats versus carbs.
Yeah. Fats provide about 37 kilojoules per gram, or 9 calories per gram. Carbohydrates and proteins are much lower, around 17 kilojoules per gram, or 4 calories per gram.
So fats pack, more than double the energy per gram.
By mass, yes. Almost 8 times as much as carbohydrates, according to the source materials numbers, using kJ. Fats are very energy dense. That's why animals, including us, store excess energy primarily as fat. It's efficient storage.
This brings us right to dieting, doesn't it?
Mm.
The seemingly simple energy balance idea. Calories in versus calories out.
That's the first law perspective on weight management, absolutely. If energy in, from food, is greater than energy out, metabolism plus activity, then the change in stored energy, delta is system mostly fat, must be positive. You gain weight.
And if energy in is less than energy out,
you lose weight drawing on stored energy. It seems straightforward. Consume fewer calories than you burn.
But we all know it's often much harder than that in practice. Why is this so complicated for so many people?
That's where the body's incredibly complex regulation and adaptive nature come into play. It's not just a simple furnace.
How does it adapt?
When you significantly cut calories, especially long-term, your body often interprets this as a period of scarcity or starvation. It doesn't know you're intentionally dieting.
So it activates survival mechanisms.
Exactly. One key response is to become more energy efficient. It can actually lower your basal metabolic rate, BMR, the energy you burn just existing.
So your engine starts idling lower.
In a sense, yes. Your body tries to conserve energy. This explains, at least partly, why weight loss often slows down over time on a diet, and why some people struggle to keep weight off afterwards. Their body has adapted to function on fewer calories.
It becomes more food efficient, as the research puts it.
Right. Which is great if you're starving, but frustrating if you're trying to lose weight.
So the body has these built-in defenses against weight loss?
It certainly seems so. There's also the compelling set point theory.
Set point.
The idea that our bodies, perhaps influenced by genetics, have a preferred range or set point for body fat percentage. Your body actively works to defend this level by adjusting metabolism, hunger signals, activity levels. If you drop below your set point, your body might increase hunger and decrease BMR to push you back up. If you go above it, it might do the opposite, though that side seems less robust for many people.
And genetics play a role in this set point, like that RI beta gene mentioned.
Research suggests genetics significantly influence our predisposition to weight gain and where our set point might lie. Genes like RA beta are implicated in energy regulation pathways. It adds another layer of complexity beyond simple willpower.
So, given all this complexity, what would be considered a sensible diet approach from a thermodynamic yet realistic perspective?
Well, one perspective highlighted in the research, acknowledging this complexity, suggests moving away from rigid calorie counting and instead focusing on listening to your body's natural signals.
Right.
Like eating only when you're genuinely physiologically hungry and stopping before you feel overly full or stuffed. It's about trying to reconnect with and respect your body's innate metabolic wisdom rather than constantly fighting against it.
It sounds simpler, but maybe harder to practice in our modern food environment?
Perhaps. But it acknowledges that the human body isn't just a simple input-output machine. It's a complex, self-regulating system.
It's still wild to think about the numbers, though. Using these concepts to estimate how long it takes to burn off a meal.
Yeah, the examples are illustrative.
Like a typical fast food lunch, maybe 2 burgers, fries, soda, clocking in around 900 food calories, kcal.
Uh-huh.
The research calculates that for an average person, just burning that off by watching TV could take over 9 hours.
Because the metabolic rate during sedentary activity is very low.
But if you went for a fast swim, you could burn those same 900 calories in less than an hour.
Shows the massive difference activity level makes to the energy outside of the equation.
And it's not just about big meals or intense exercise. Small changes add up too, right?
Absolutely.
Yeah.
The example of switching from regular potato chips to a fat-free version.
Saving maybe 75 calories per serving. Seems tiny.
Seems tiny, yes. But do that regularly, say once a day for a year. That's over 27,000 calories saved.
Which translates to...
Since body fat stores about 33,100 kiloj, or 7,800 cal, per kilogram, that saving could theoretically lead to losing several kilograms of body fat over the year, assuming everything else stays constant.
Wow. It shows how those small, consistent energy imbalances, positive or negative, really compound over time. It's pure energy conservation playing out.
Exactly. The first law is relentless.
Finally, we should probably briefly touch on the body mass index, or BMI, as mentioned in the material.
Right, the BMI. It's a very common tool used in health assessments.
How's it calculated?
It's quite simple. You divide a person's weight in kilograms by the square of their height in meters. Weight, kilogay, height, M2.
And it gives a single number. What does that number mean?
It's used as an indicator to categorize weight status: underweight, healthy weight, overweight, obese. A BMI between roughly 18.5 or 19 and 25 is generally considered the healthy weight range for adults.
So it's a quick screening tool.
Exactly. It's not a perfect measure of body fat or health for everyone. Very muscular people might have a high BMI without being overfat, for instance. But it provides a simple, scientifically recognized way to assess weight relative to height for large populations and generally for individuals. It's grounded in those same fundamental principles of mass and scale that we see throughout physics and engineering.
We've certainly covered a lot of ground today. We've journeyed through the core concepts of energy analysis in closed systems.
From the nitty-gritty mechanics of boundary work that powers our engines,
to the incredibly intricate and, frankly, beautiful energy transformations constantly occurring within our own bodies.
It's quite a range.
And the underlying principle, through it all, energy conservation. The first law. It's simple conceptually, yet so profoundly powerful and elegant.
It really is. It explains phenomena across vastly different scales, from tiny gas molecules to huge industrial plants, and yes, even our own biology. It's a truly universal law.
So maybe next time you're feeling a bit sluggish, or you're just wondering how your morning coffee or that quick snack is actually powering your day.
Yeah.
Take a moment to consider the incredible unseen energy transformations happening within you. You are, in effect, a beautifully complex closed system, constantly operating by these fundamental thermodynamic laws.
It puts a different perspective on things, doesn't it?
Hopefully you now have a much clearer lens to view the world through, and maybe a deeper appreciation for how energy truly works, especially in these closed systems. So here's a final thought to leave you with. Now that you have this framework, what other surprising aha moments about energy conservation will you uncover in your own daily life? Where else do you see these principles at play?